Welcome to Pavements, webinars for the pavement community. I'm Andrew Braham, and today we'll be talking about the development of a field measuring device to establish return to traffic for full depth reclamation pavements. This presentation is built off of work done by Robert Hill. Robert Hill's master's thesis was titled Return to Traffic of Full Depth Reclamation Pavements, and he obtained his Bachelor's of Science in Civil Engineering from the University of Arkansas in 2011, and he obtained his Master's of Science of Civil Engineering in 2013. And you can see his link provided there to LinkedIn, which is also down in the comments section. Now, throughout this presentation, you will see a couple of acronyms repeated multiple times. One is CIR, and that will stand for Cold in Place Recycling. And the second is FDR, and that stands for Full Depth Reclamation. And you can see the picture on the right is a picture of full depth reclamation being placed in the field. The objective of this research project was to develop a test to determine when CIR and FDR projects are ready to release to traffic. And this is because raveling problems can occur if traffic is released too soon onto the CIR or FDR surface. And there is no current test available to try and quantify this time to return to traffic. Now, for the rest of the presentation, we will focus simply on FDR, or full depth reclamation. Now, the research objective was to develop a test to determine when you can release to traffic, but we wanted this test to be simple and inexpensive so that it could be run by agencies or owners in the field during their projects. Now, the definition of FDR is that it is a recycling method, and what happens is you can take an existing pavement structure. So on the left you see an overlay on top of a deteriorated hot mix asphalt surface, and there's some old base underneath those two layers and then some subgrade. And what you do is you pulverize and mix the bound material, which is the overlay and the HMA in the image, and you also have some unbound material, which is the old base and can even be the subgrade. So you pulverize and mix all of that together with some sort of stabilization agent. And what this creates is a new FDR layer, and this is what is called a stabilized base course. Then you need to place some sort of surface on top of that FDR surface. Now, the existing pavement, the existing bound pavement, can have many different types of distresses. Pretty much any type of cracking, all the way from age, fatigue, or edge cracking to slippage, block, longitudinal, or reflection cracking. You can also address ride quality, which includes bumps and localized depression, various types of permanent deformation, rutting, shoving, and washboarding, and then other types of general deterioration, including raveling, potholes, stripping, and delamination. And all of these distresses can be associated with an inadequate structural capacity. And because you're pulverizing and mixing both bound and unbound material, what you're doing is you're actually increasing the structural capacity of your existing roadway. Now, we also mentioned that you need to add some sort of stabilizing agents, and there's three types of FDR. One is simply mechanical, and that's where you use a granular material which is angular enough in order to have that interlocking nature to provide structural capacity. Or you can add some sort of chemical stabilizing agent such as Portland cement, calcium chloride, hydrated lime, or coal fly ash. Or you can have a bituminous stabilizing agent, and that can be either a slow or medium set asphalt emulsion, or you can have foamed asphalt binder. And as mentioned before, once you've stabilized your pulverized and mixed bound and unbound layers, you place a wearing course on top. And that can be an asphalt concrete overlay, it can be slurry seal or microsurfacing, chip seals, or various other types of surface treatments. With that brief background on FDR, this is what we'll be talking about today. And we're going to start out with talking about the mixed design of full depth reclamation as followed in this project. So the first consideration was the gradation, and for this research we used RAP, which is reclaimed asphalt pavement, and then we used AHTD class 7 unbound granular material. And you can see the gradation of the RAP and the AHTD class 7 material in the graph. And you can see the blend of those two materials. And the object was to get that blend in between the maximum and the minimum gradation blends. And those maximum and minimum gradation bands were from the South African report on full depth reclamation, also called TG-2, which was released in May 2009. Now, in addition to the gradation for the mixed design, we also looked at the optimal moisture content. Because we're using both bound and unbound materials, we need to figure out how much water needs to be added in order to achieve the maximum unit weight. And so we used ASTM D1557, which is a modified Proctor test, and testing at various water contents, we found our optimal moisture content to be 5.4%. With our gradation and our optimal moisture content, we next tried to find our optimal emulsion content. In order to do this, we measured both the theoretical maximum specific gravity and the bulk specific gravity of the FDR mix. And then we performed ASTM D4867, which is the indirect tensile test, and we tested it in both the dry and the conditioned, also known as moisture conditioned state. And by knowing the maximum specific gravity and the bulk specific gravity and these two tensile strengths, we were able to calculate the optimal emulsion content. So you can see here on the top curve, the squares are the unconditioned or the dry ITS, indirect tensile strength tests. And on the bottom, the diamonds or the conditioned samples, the moisture conditioned samples were on the bottom. And from these two graphs, we wanted to estimate what the optimal emulsion content was, and both of them were at a maximum of around 4% optimal emulsion content. Now, optimal emulsion content does include both the asphalt binder and the water component of the asphalt emulsion. And since we were using a 63% residue, which means that 63% of the asphalt emulsion was asphalt binder, we needed to ensure that when we were making our samples, our optimal moisture content included both added water and the water in the asphalt emulsion. Now, with the mix design completed, we had our reclaimed asphalt pavement and our class 7 unbound aggregate. We had our optimal moisture content and our optimal emulsion content. We were able to start working on our in-house testers. When we're thinking about returning to traffic, we thought there were 4 different mechanisms that could be incorporated into trying to quantify if a surface is ready to be returned to traffic. And that included testing the friction of the surface, the cohesion of the surface, some sort of sweeping or brushing mechanism against the surface, and then the rebound or the stiffness of the surface. So these are all concepts that could potentially quantify whether a surface is ready to have traffic return to it. Now, these were all meant to mimic what was happening in the field, and then in order to correlate this to a lab test, we chose the Raveling test. And you can see that in the picture on the right, where there is a sample of FDR with a rubber hose that abrades over the sample of that surface, and you see how much material comes off of this top of that surface. And we'll be talking more about the Raveling test a little later. So let's go through those 4 concepts behind the testers that are listed. And we'll start with friction. So when we thought about friction tests, we thought about the British pendulum tester, or the BPT. And this is able to quantify friction in the field of a surface. It's simple to use, And it has a very easy protocol. You simply place that piece of equipment and swing the arm to see how far it rebounds upwards. It's a relatively small cost, and you could potentially adapt it to gyratory samples. Now, some of the cons to it is that it is a relatively low speed device, so the traffic has to be moving slowly, and you're looking at micro texture rather than macro texture of the surface. So usually the BPT is looking at the friction on a very micro level, but FDR, if it has large enough aggregate, you may have some macro effects there. So that's something to take into account. Now, one of our original objectives was to develop a tester that was easy to use and was a relatively low cost or inexpensive piece of equipment. So our tester that tried to mimic the British pendulum tester looked like this. And what you do is you set your angle of content, so how far you bring that blue bar up, and then you simply drop the bar. And you drop it twice. And on the first drop, you see how many times it swings back and forth. And then you simply repeat the test and you take a ratio of those numbers of swings. So if on the first drop you have 6 swings, and on the second drop you have 7 swings, you have a ratio of 0.857. Now the second concept behind the testers were cohesion, and we looked to a slurry seal or microsurfacing device called the cohesion meter. And there's a picture shown there. And this is torque driven. You apply a torque on a sample, and the sample is the round black sample in the middle of that testing device. You measure the torque required in order to make a deformation on the sample. And you do both a visual inspection to measure the cohesion, and also you take the actual torque reading off the torque bar. In order to make a similar device for field use, you can see here what we did is we developed our own in-house cohesion measuring device. And the picture on the right, you can see the screws at the base of the piece of equipment. Those dig into the surface, and what you do is you have 2 people stand on the 2x6s and you try and twist that in the pavement. And you apply about 192 pounds of torque, and what you do is you look at what is the maximum amount of torque that is read from the wrench when you start twisting in order to obtain failure of the sample of pavement. So once it starts moving in the pavement, what sort of torque do you have that's being applied to the pavement? And we found that about 192 pounds was the limit before you could start seeing deterioration of the surface. Moving down the different concepts, the next was the friction tester, and we modeled our in-house tester based on the dynamic friction tester, or DFT. Now, some pros of this test are it has good reproducibility, it's very compact and has a short measuring time, and you can also vary the speed. So there's a little brush underneath that machine, and you can vary how quickly that brush moves. However, it is a relatively large piece of equipment, so it's difficult to test on laboratory samples, and it's also relatively expensive. And finally, you need to have both a water tank and a portable computer in order to run the tests. So there's a decent amount of peripheral equipment. So for our in-house friction measuring devices, we simply made a small wooden frame, bought just a normal like power drill, and then attach this simple broom to this end of that power drill. And you activate the power drill, and that rotates the broom, and you're able to get some friction measurements. And you want to sweep the surface for 45 seconds, and you can measure the initial mass of your sample or area and then what your final mass is, and you can get a percent mass loss. So as that broom goes over that surface, you're able to quantify how much material is lifted from the surface, and that gave us an idea of whether or not you were able to return to traffic. Now, the fourth concept that we did was a stiffness measuring device, and what we were thinking about here was the falling weight deflectometer. And the theory was, as the asphalt emulsion or asphalt foam gains strength, the stiffness will increase, and we'd be able to see that through a falling weight deflectometer or equivalent equipment. So what this can do is it can estimate the pavement structural capacity, and what you do is you tow a little portable unit behind a truck, you drop a weight, and you measure how the deflections occur as you move away from that weight. And what we're trying to do here with the FWD is to simulate a rolling vehicle wheel. Now it is relatively expensive, the analysis technique is quite complex, and if you have inhomogeneous pavement underneath, it can be challenging because as you can see on the image in the left, when you drop a weight, a wave goes out. And if you have an inhomogeneous mixture where those little uh, devices are placed on the pavement away from the weight, if they're on some sort of aberration in the pavement surface, you could get an erroneous reading. So those are things that you just want to keep an eye out on. And our in-house tester was simply a plastic pipe that was placed on a surface, and we drop a golf ball 3 times. And you move the device slightly after each drop, and you simply measure the rebound height, and you take the average of 3 drops. And the theory is if you have a stiffer mixture, then the rebound height will be higher. If you have a less stiff mixture, the rebound height will be lower. And you're trying to quantify whether you can return traffic to that road. These are the 4 different concepts behind the testing, and then we wanted to correlate it to an existing lab test, so we chose the Raveling measuring device, and this Raveling test is from ASTM D7196, and what this does is it measures the mass loss. So you have that hose abrading on the surface, you take the sample, the weight of the sample before the test and the weight of the sample after the test, and after that hose has abraded the surface, you can measure how much had raveled off. This gives you an idea of the curing rate. Now, because FDR does not gain strength as quickly as CIR, which the Raveling test was developed for CIR, we actually performed a modified test. And instead of measuring the amount of material loss, we measured how long the sample stayed intact, and that was in seconds. Because as that rubber hose started abrading the surface, often it would literally explode and there would be no more raveling because you weren't abrading the surface, but you would have lost a lot of material. Now, once that state was reached, we measured how much time had passed or how long the sample lasted. Now, with our in-house tester designs completed, we then moved on to our testing matrix. And you can see we looked at different curing times. We looked everywhere from 0 to 48 hours. So this is for both asphalt emulsion and asphalt foam. We looked at curing samples at both ambient temperatures, so just sitting out on the ledge, and at 40 degrees Celsius in a draft oven. We had different levels of the number of samples depending on the test. Some testers had 2 samples, some had 3 samples. As I mentioned, we looked at both asphalt emulsion and asphalt foam. And then we looked at the 5 tests, the rebound, the sweep test, the torque test, the pendulum test, and the raveling test. So in total, we tested 210 samples in a partial factorial, and this allowed us to look at the influence of curing time and the curing procedure and the type of stabilization on the result of the testers. Now, for some data analysis, we looked at the 5 testers, and for this first round, we only looked at 48 hours curing at ambient temperature. And we found that there were promising results for the brushing tests. You can see here over time the mass loss decreases, which is what you would expect. And also the modified raveling and the stiffness. So for the modified raveling, as time passed, the time until the sample failed increased. And for the stiffness, as time passed, the stiffness increased. And when we say the results were promising, that meant that based on a p-value at 95% significance and the coefficient of variance, we were seeing statistically significant changes in the sample over time. Now, 2 tests were not promising. They had poor results, so we didn't pursue these because we didn't see statistically significant changes over the 48 hours at ambient temperatures. And that included the cohesion test and the friction test. Now, the 3 promising tests, the brushing, stiffness, and the modified raveling, we moved those forward for additional testing. The first was looking at, again, a 48-hour ambient temperature cure for both asphalt emulsion and foam. So you can see here the foamed samples had a higher mass loss during the brushing test. They had a lower stiffness and a lower time until failure in the modified raveling tests. So from these three sets of data, we determined that we thought asphalt emulsion appeared more resistant to raveling in the field. Now we also looked at different temperatures, looking just at asphalt emulsion because we felt that asphalt emulsion appeared more resistant to raveling. We tried it at two different curing temperatures, and you can see here at 40 degrees Celsius we had a decrease in percent mass loss during the brushing test. The stiffness was approximately the same, and the modified raveling we had a shorter time to failure for the 40 degrees Celsius. And we felt that there was a significant difference for the brushing and the modified raveling. And although that modified raveling may be a little unintuitive, because we tested the sample at 40 degrees Celsius, we felt maybe that higher temperature decreased the amount of cohesion that was building within the sample. So there's still some things to look at here, but the trends did seem to make sense. And we found a significant difference for the brushing and the modified raveling tests. So from this preliminary research and these initial conclusions, we found that the data that we obtained was fairly inconsistent. We found some good trends, but we had difficult actually proving they were statistically significant. And we feel that may have come from the devices being a little too simple. We were aiming for inexpensive and easy to build devices, and we may have swung too far in that direction. However, from this initial data, we did feel that the raveling test and the sweep test showed the most potential. So we feel that there could be some areas that we could move forward in those two tests, perhaps with a little higher quality equipment and a larger experimental matrix. And we think that when we're looking at raveling, we should be looking at mass loss. So trying to figure out how much material comes up during these tests in the field or in the lab is a good way to quantify the potential to return to traffic. Now, we definitely feel that this initial work is the first round of device evaluation, and we definitely recommend that there are further work done on each of the devices to continue to evaluate their suitableness for a return to traffic testing device. So some recommendations for future research: we do suggest better construction, put a little more money into each device, modify them, and test them a little more. We believe that the sweep and the raveling tests are the most promising, but we do feel that there are other areas that should continue to be explored beyond just those two tests. And then finally, you can see we did go out into the field with some preliminary devices, but most of our work was simply done in the lab. So we definitely recommend that we tie some lab test results to actual field performance, and that will be the critical link in order to develop these pieces of equipment. So if you're interested in learning more specifically about asphalt emulsions, I recommend you go to training.uark.edu and you search asphalt emulsion. And also you can read the full paper about this research. We only covered the highlights in this presentation, but you can read the full paper here from the Journal of Testing and Evaluation. And again, the links for all of this are available below in the description. Thank you very much. We appreciate your time.